Alright, hello everyone and welcome. In this video, I'm going to be explaining the CHM236 practical. And I'm not going to write anything, I'm not going to type anything, just follow me from your manual. So it's almost the same thing in your manual. So all these theoretical parts, you're going to read that by yourself. I'm just concerned about the calculation aspect of it. So the first one is the determination of calcium and magnesium in tap water. So the first thing actually, is standardization, because what you will use to find the percentage or the determination of calcium and magnesium is actually your EDTA. But you have to standardize it first. That is, you have to know its concentration first. And from this, you are supplied with sodium disodium ethylene diamine tetracetic acid, tetracetate dihydrate. So you are now going to standardize the EDTA using 0.01 molar zinc sulfate heptahydrate. So you are going to standardize your EDTA using the standard solution. So you are going to add ammonia buffer and 2 drops of erythrol black. So all you have to do is to set up your titration stand, put a known volume of your standard solution, maybe from your pipette if it is 20 or 25 cm cube. So you're going to put that here first. Then you add 2 cm cube of ammonium buffer solution. So the function of this ammonia buffer is to keep the pH fairly constant. That's just the meaning of buffer solution. They are solutions that resist a significant change in pH. And your titration must be kept at a particular pH. So that's why you have to add buffer solution, and then 1 to 2 drops of erythrol black indicator. So after you add your ammonia buffer, you still add your your indicator. Alright, so after that, then you now titrate. Your EDTA that you want to standardize will be in your burette. So you now standardize. How do you standardize? Then you titrate. So you say you find the first titer value, second titer value, and third titer value, divide by 3. And you can use 1 and 2 if you have done rough before. Alright, so from here you will get your V of EDTA now. That is the average volume of EDTA used. So the same setup will be used 3 times. You put this first, this and this, then you titrate. The volume you get your first one, put this again, pour that one away, then this, do it again second, and for the third time. So you find the average, divide by 3. The volume you get, say for instance 40 cm cube, is your volume of EDTA. Now EDTA is reacting with something here. It's not actually zinc sulfate it is reacting with. It's actually reacting with the zinc, because zinc sulfate in solution will dissociate to give zinc 2 plus and SO4 2 minus. And EDTA will always react with metal. So is this zinc 2 plus part of this solution of zinc sulfate that the EDTA will react with? And zinc or any metal will react with EDTA in 1:1. So it will always be in 1:1. So which means that the number of mole of EDTA or number of mole of zinc will be equal to the number of mole of EDTA. So that means you can say that number of mole, which is Cphi, it is concentration of EDTA times volume of EDTA, will be equal to concentration of the zinc, the metal, times the volume of the zinc 2 plus. Now this is like using CaVa over CbVb equal Na over Nb, because like your A you can call it EDTA and your B you can call it the zinc, because they have the same number of mole, 1:1. So it means if you are still cross multiplying, you have this equal to this, something like this. Okay, and you're asked not to use this formula. You're asked to use what we call the mole concept. So how do you use the mole concept to solve this kind of problem? Normally the answer you will get when you use this is going to be, you want to standardize, that is, you want to find the coefficient of your EDTA. Coefficient for EDTA will now be coefficient of zinc, which is 0.01 given to you, is in mole per dm cube, then times the volume. So the volume should be in dm cube as well. So that will be 25. Okay, that's the volume of this stuff. Okay, that you put a 25 over 1000. Okay, then divided by your VE, volume of EDTA, which is 40. Okay, over 1000 as well, 40 over 1000. I hope that's taken. So that's how you get your condition. But normally you're not supposed to do it like that. This is the way you're supposed to do it. You're going to say, and you'll see that we're going to get the same thing. So using the mole concept, let me get rid of this first. You know that 1 molar means 1 mole per dm cube, and if you have 2 molar, it means 2 moles per dm cubed. So that's just the meaning. Okay, so in that 0.01 molar of zinc sulfate, okay, it means that we have 0.01 mole, okay, in 1 dm cubed. Now because our volume was measured in cm cubed, so we are going to turn this dm cube to cm cube, and 1 dm cube is actually 1000 cm cube. So that means 0.1 mole of zinc 2 plus is present in 1000 cm cube of solution. Okay, I call it zinc 2 plus and not zinc sulfate because it is only the zinc 2 plus that is actually reacting, and they will have equal number of mole, because for every 1 mole of zinc sulfate that dissociates is going to give rise to 1 mole of zinc 2 plus as well. So we know that 0.01 mole of zinc 2 plus is present, okay, is present in 1000 cm cube. Then how many mole will be present in this 25 cm cube that is reacting? Okay, so that is the number of mole of zinc 2 plus that is reacting with that EDTA now, and that is going to be 25 times 0.01 over 1000. Okay, then since metal and EDTA react in 1:1, it means that this number of mole of metal zinc 2 plus that reacts, okay, will be equal to the number of mole of sodium, of EDTA as well. So from here we can say that the number of mole of EDTA will now be equal to this, which is 25 over 1000, okay, times 0.01. Now if you want to know its concentration, concentration is now number of mole over volume, which is this divided by what? Divided by the volume, and the volume is the theta value, which we said to be equal to 40 cm cube after you find the first plus second plus third divided by 3. So then divide by 40 cm cube, that is 40 times divided by 1000 in dm cube now. But still you not use this formula. What you would say is that this is the number of mole, right? So it means this number of mole, when you calculate it, I don't know, that should give you 1, 2, 3, 4. So that should give you 0.00025. Okay, that should be the number of mole. So you're going to say that to be equal to, that's the number of mole. That's the number of mole of EDTA as well. So that is the number of mole that is present in that 40 cm cube. Okay, because this is the volume of EDTA that reacts, and this is the number of mole of EDTA that reacts. It means this number of mole of EDTA is present in 40 cm cube. Now in 1000 cm cube now, what will be the number of mole that will be present? The number of mole that is present in 1000 cm cube is that actually the molarity. The number of mole in 1 dm cube or 1000 cm cube. So that's how to calculate the concentration like that using the mole concept. So the number of mole you get here is now it's like the concentration now, because that will be the number of mole in 1 dm cube. So if you want to get the concentration now of EDTA, that's now going to be what? That's going to be 1000 times 0.00025 over 40. So that's like this. So your x, okay, the condition of EDTA now will be 0.025 over 4. That is going to be x equal 0.0063 molarity. That is, molar. So that is the condition of your EDTA. Now you are be able to standardize the EDTA, and simply you can use the formula CAVA equals CBVB to get your accurate answer if this is not clear to you. But this is how you are supposed to do it in your manual. So just watch the video again if you do not get it. Now that is just the standardization aspect of it. So the next thing now is to determine your calcium and magnesium jointly. Now carefully measure 100 cm cube of tap water. Okay, so you put 100 cm cube of tap water, you put it here, 100 cm cube of tap water. Then you add 2 cm cube of ammonia buffer, of course you know the function of that, and 1 to 2 drop of solochrome black, that is your indicator. So you add that one too. Then titrate with the standardized EDTA. So the EDTA that you have standardized, you have known its consolidation, then you standardize, like you titrate with it. So the aim is that you know the condition of EDTA already to maybe 0.0063 molar. Then the volume will be the volume of EDTA used, because it is the one that you are titrating with. So that will be volume of EDTA. We don't know it. Let's say it is 40 cm cube. After 4 seconds, our third titration has divided, so maybe you get 40. Then the next thing now, is that you want to calculate what is actually reacting in this water is calcium 2+ and magnesium 2+. Not the water actually, is the metal part of the water that will be reacting with the EDTA, because EDTA always reacts with metal, and water is hard because of this calcium and magnesium that is present in it. So those are the ones that will react to the EDTA. So you want to know the condition of these two guys too. So that's what you don't know. Then the volume of the metal, condition of metal of these two guys is what you don't know, and the volume, that's what you want to actually determine. The volume is actually 20. No, it's not 25 in this case. It is actually 100 cm cube, because you pour 100 cm cube of water. So since you know that this one will react in ratio 1:1 to the to the EDTA, you can actually say that condition of these two metals times the volume, which is of that metal, will be equal to condition of the EDTA then times the volume of the EDTA. You can do it that way, okay? But that is just to get the answer. We don't normally do it that way because we have to use the mole concept. Now to use the mole concept, it's still the same step as we followed the last time. Okay, so let me just do it. So it's still the same step we are going to follow. So all you have to do is that you have to find the number of mole of this guy first, the EDTA. This is the condition of EDTA, and this is the volume of EDTA used, assuming that's what we assumed. So I'm going to say that 0.0063 mole of this EDTA is present in 1000 cm cube. That's just the meaning of this. Then how much will be present in 40 cm cube? So X will be equal to 40 times 0.0063 over 1000. Okay, so when you press that in calculator, you are going to get, so this gives 0. Let me create some space. So this gives 0.000252 mole. So that is the number of mole of EDTA that actually reacts. Okay, and it will be equal to the number of mole of these two guys too, the metal that reacts. So that means the number of mole of this M, which is the two metal, okay, will be equal to 0.000252 mole. So now to find their concentration, now you are going to say, this is the number of mole that will be present in this volume of water that you add. Okay, so that means that 0.000252 mole of this metal is present in 100 cm cube of water that you add. Then how much will be present in 1000 cm cube? That is their concentration now. So X will be equal to 1000 times 0.00025 over 100. So that will be 10, and X will be equal to 0.0025 molar now. So that's the concentration of the 2 metal in water. Now to get for calcium only, that is for the 2 metal. Now to get for calcium only, then to 100, that is in your manual, to 100 cm cube of water, of tap water, okay, you still add it there again, 2 cm cube of diethylamine, or you use 2 cm cube of sodium hydroxide, you should add that one. So the meaning of that is that you want to use that as a masking agent, because you want to determine the concentration of calcium only now, and in your tap water there will be calcium and magnesium. So you are going to add masking agents to render that magnesium unreactive. Masking agents will not, is a way of making something not react. You will not remove that thing physically from the solution, from the reaction medium. You just add some reagent that will turn it inactive so that it will not react, and those reagents are called the masking agent. For different metal, we have different masking agent for them. So for magnesium, one of them is sodium hydroxide. So if you add sodium hydroxide, it will turn the magnesium into something that will not react. So after adding that, you add 2 to 3 drops of silicon dark blue indicator. So that's just the function to indicate when the reaction has ended. And you titrate with the standardized EDTA. So you're going to titrate with the standardized EDTA as well. This is your burette. So you're going to put your EDTA here. Now your EDTA, you still know the concentration already. So the concentration of EDTA, as you standardize is the other time, was, let me check, 0.0063. So that's the concentration of EDTA, 0.0063 molar. Then from after the titration, you are going to get your volume of EDTA. That is going to be, let's say, 40 cm cube. Of course, you will have gotten this from your practical. Now the volume of your metal now, that is the volume of your analyte, which is metal, of course, but the total volume is 100 cm cube, because that's the volume of water that they are present in. Then you want to calculate the concentration of that metal now. Remember, it is only calcium, so the concentration now is what you want to find. So you use the same formula, the same method. You say 0.0063 mole of EDTA is present in 1000 cm cube. How much will be present in 40 cm cubed? Okay. So from here you get X to be equal to, your X will be equal to 40 times 0.0063 all over 1000, and that is going to give us 0.0063 times 40 divided by 1000. So that gives 0.00252. Oh, we use the same theta value, of course, but you will have gotten a particular theta value in your question. This is how we get, and it doesn't even make sense for me to use this 40, because the amount of EDTA that will react with this water will be different from the one that will react with that water here, okay, with this one. So I'm not supposed to use 40 here. It doesn't make sense. So because we have masked magnesium, so let me use something like maybe 30. Okay, let me use like 30. And will it be 30? Let us reason it, because the amount of thing that will react now is that it has actually decreased. So that means the number of molar has decreased, so that should affect the volume as well. So the volume should decrease. It makes sense. So the volume will decrease actually. Now, so let's say it is 30. We should not get the same answer actually. So that should be 30 times 0.0063 divided by 1000. Good. So X is now equal to 0.000189 mole. So that is the number of mole of EDTA that reacts. Okay, since it will be the same as the number of mole of calcium, they react in 1:1. So that means that 0.00189 mole of calcium will be present in that volume of water you add, which is 100 cm cube. Then how much will be present in 1000 cm cube now? So that will be in 1000 cm cube, how much? So that's going to be in molarity. Okay, so that's going to be 1000. Does this thing make sense? It does. So times 0.000189 divided by 100. So this cancels, so we have x to be equal to 0.00 189 molar. So this is the amount of calcium alone in water. So that's the number of mole of calcium alone in water. So if you want to determine, now the question is that calculate the amount of calcium and magnesium separately in milligram per liter in tap water. Now if you check the previous question, we got this mole, this answer. Let me check. Yep, we get this answer for the what? For the calcium and magnesium, jointly. That is the number of that's the condition we got, and that is 0.0025 molar for calcium and magnesium. Now we got for calcium only now to be equal to 0.00189 molar. So that is the amount in mole in 1 liter. So it means that in 1 liter we have this number of mole of calcium and magnesium. That's just the meaning. And in 1 liter we have just that of calcium to be this. So how much in 1 liter will now be for magnesium alone? So that means it will be for magnesium alone, the number of mole in 1 liter, which is its molarity, will be 0.0025 minus 0.0018 molar. So for magnesium alone, the number of mole will be 0.0025 minus 0.00189. So that gives 0.00061 molar. So that is the number of mole, in 1 liter, or let me say the molarity of magnesium, and this is the molarity of calcium. So you're not going to solve for, you want to get it in milligram per liter, and you have gotten it in mole per liter now. So it's very easy. So to convert, that means we have this mole, 0.00189 mole of calcium in 1 liter. So you want to calculate it in milligram per liter. So that is going to be 0.00189 times. Now that is the number of, if you want to convert it to mass, number of mole is mass over molar mass. Okay, to get the mass now, it will be what? Number of mole times molar mass. So if you want to get the mass equivalent now, you just multiply this number of mole times the molar mass of calcium, which is 40. That will give you in gram over 1 liter. Then to convert to milligram now, if you want to convert to milligram, so that is going to be what? So to convert to milligram, let me check. That's going to that's going to be times 1000. So you stick it times it by 1000. So that's going to be 0.00189 times 40 gram, then times 1000. That's going to turn to milligram per 1 liter. So the same thing you are going to do here. Magnesium, I think, is 24. So for magnesium, it is going to be 0.00061 times 24. That's going to turn into this gram, to 8 gram over 1 liter. Okay, which will be what? 0.00061 times 24. Okay, then times 1000. Alright, then divided by 1 liter. So that doesn't make any change. Okay, so this is going to be your answer in milligram per liter. So whatever you get here, so let me do it. 0.00061 then times 24 times 1000. Alright, divided by 1. So that gives 14.64 milligram per liter. And for this, if you do it, you have 0.00189 times 40 times 1000, that's going to be in milligram per liter also, and that gives 75.6 milligram per liter. So sometimes they might ask you to find it in parts per million, that is in ppm. Find the amount of magnesium and calcium in ppm. It's still the same thing as the milligram per liter. So milligram per liter is still the same thing. So you can say that the amount of calcium is now 75.6 parts per million, and the amount of magnesium is now 14.64 parts per million. So it's still the same thing. So that's how you can determine the amount of calcium and magnesium in water. Thanks for watching.